Dave. All right, thanks everyone. All right, so like Chad introduced, I'll be talking today about evolution of morphology and composition during annealing and salinization of solution process CZTS. And I'm happy to present this work today. It was, this is actually a recently published, or accepted, excuse me, in Chemistry of Materials. It's about a week ago, so I'm really excited that that got accepted. Thanks, appreciate that. So yeah, so before I get into that data, I wanted to give a little introduction about the state of solar energy as it is right now in the world. So this was the picture as of not too long ago. What you're looking at here is the price of electricity as it relates to parity. And what that means is the price of electricity per state as it, generated from other sources. And at $3 a watt for utility scale PV, you can see in most states it doesn't make sense to install solar panels. But the price of electricity or utility scale PV has rapidly dropped in just the past 7 years. This is 2010 to 2017. It's gone from $4.50 per watt down to $1 per watt. And if you look at what this does in terms of this parity map here, at $2 a watt, it becomes economically sensible to do it in the Southwest. And at $1 per watt, almost every state, with the exception of our home state of Washington here, it makes a lot of sense to install utility scale PV. But the issue is it's only like 1% of the total electricity generation by fuel source. And which, when you look at it closely, that's less than wood. We're not getting that much electricity from solar panels as it stands right now. It's about 1% of what's out there. So the big question is what is preventing, what's stopping solar energy from becoming more prevalent? And a big part of that is the capital expenditure of what goes into building a solar panel manufacturing facility. So this is called CapEx. And it's the upfront cost with associated in building a manufacturing facility. It's not just the equipment, but like the engineering costs and the taxes and the land. There's a lot of things that go into CapEx. So there's been some estimates by Powell et al. Here. This looked at different prices or the amount of capital investment required for different absorber technologies for different absorbers. And crystalline silicon, which is the most prevalent technology, it's about $1 per watt CapEx that you need to invest up front to build a gigawatt year production solar factory. For thin film technologies, it's about 20% less with $800 million investment required. But it's estimated that for solution processed absorbers, from roll-to-roll style processing, you could get that price down to $60 million, so more than an order of magnitude lower. So this would be a game changer. If we could somehow get a 15% module that's roll-to-roll printed, it would have an enormous impact in the global PV market. Everyone would be able to jump in and invest in these in solar manufacturing, and that's what we're working at here at UW at the Clean Energy Institute. We have this roll-to-roll printer here where we can work out the physics and chemical processes that are required to make these high-efficiency solar PV devices at scale. So what we focus on in the Hillhouse group is thin film chalcogenide absorbers, particularly solution process. That's one of the things that's focused on in the Hillhouse group. And thin film solar cells have the advantage of being much thinner by name than like silicon solar cells. And this has like a lot of surprising implications. Like one of the big costs for solar cells is the actual support you need to hold it up. So if it's 100 times thinner, it takes up less space and there's less investment in that way too. But right now, they only represent about 10% of the market. This is the added capacity in 2016, about 70 gigawatts of capacity in 2016, and only about 5 of that was from thin film solar cells. And the reason for that, or one of the reasons for that, is because there's long-term questions about the supply of these two leading thin film technologies, cadmium telluride and copper indium gallium selenide, or CadTel and CIGS. They have a maximum theoretical efficiency of about 32%, and they're achieving efficiencies of about 20%. So what we're looking at is an alternative technology that has a much higher earth abundance. The efficiency isn't quite there yet. It's a newer technology. But if we're able to improve the efficiency of CZTS, it could be a game changer. It could be a terawatt level technology because it can scale up because of the high crustal abundance of these elements. So I study solution process CZTS, and the world record, like I said, is 12.6% efficient. But it actually uses The solution process to make this world record device uses hydrazine as a solvent, which was pyrophoric, carcinogenic, and is literally rocket fuel. So this kind of like defeats the purpose of having a solution process absorber if you're going to have all this safety technology, and like it's going to significantly increase the capital investment. So in the Hill House lab, we've engineered a process that uses a different solvent, uses DMSO as a solvent, and has produced devices up to 11.8% efficiency. This is the world record hydrazine-free solution process, CZTS, which is pretty comparable to the hydrazine solution process. And it's been widely adopted, but the issue is a lot of other groups find that they get these fine grain layers whenever they use this DMSO molecular link process. And for over a year, I had a lot of issues with not understanding what was causing these fine grain layers. So what this talk is about, and what my recently accepted paper is about, is what are the physical and chemical processes that are leading to these multi-layer CZTS morphologies from the sink. So to dig in on that, I'm gonna walk you through every step of what it takes to make a CZTS device from the molecular ink, and we're gonna go through step by step on what effects these have. So we start with the DMSO molecular ink, and we spin coat it and anneal it at the lab scale. You can imagine other scale-up ways to deposit this ink, but we get a metal sulfide film here, and then we go through a salinization step where we heat with selenium vapor at around 500 degrees Celsius. And then after that, we finish the device with a number of steps that I'm not going to go into. But these are the 4 major steps that are involved in making a CZTS film. And what I'm going to be focusing on in this talk is looking at different anneal times and temperatures for this spin coat and annealing step, basically this metal sulfide formation and all the impurities that come with it. And so, and these 4 steps is what we're going to be looking at throughout the process. We're going to start with the ink. We're going to start from the beginning. So this ink is composed of complexes of metal salts complexed with the DMSO and water molecules that are in solution. And if we look at thermogravimetric analysis of this ink, which is basically looking at the mass loss of this ink as a function of temperature, what you can see is that there's some clear regimes of mass loss here. If we do a mass balance on the as-added constituents, which isn't showing up too well, unfortunately, you can see that what's important, actually, is that the CZTS is showing up. And you don't ever really reach the CZTS level until well above 550 degrees Celsius. At this higher temperature here, there is some decomposition reaction that will happen, as shown. So this is even convoluted with that. And what this is saying is that at these highest temperatures, there are some impurities that remain in the film that we have to facilitate their removal somehow. Moving on to X-ray diffraction. So for people that aren't familiar with X-ray diffraction, this is basically the Fourier transform of the 3D electronic density inside of a crystal. And it gives you a fingerprint for a particular material based on these relative intensities of these peaks. So you can see the CZTS fingerprint down here at the bottom, and you can see the different peaks corresponding to CZTS. So we're forming different amounts of crystalline CZTS depending on the anneal profile. You can also see the molybdenum peak here because of the substrate. And if we zoom in on the 112 peak of the CZTS, what you see is increasing crystallinity of the CZTS with increasing anneal time and anneal temperature. At these low temperature anneals, you don't see much crystallization at all, but for the higher temperature anneals, with increasing time, you see more and more crystallization. If we move on to the selenized film, we see that we form crystalline CZTS SE for all cases. We've incorporated selenium now, but what you see is a peak shift with increasing sulfur, which indicates increasing sulfur content for these higher anneal temperatures and higher anneal times. And you can tell that from the peak shift towards higher 2 theta, which is representative of the CZTSE peak. So moving on to another way to look at the phase composition of the precursor film is you can use Raman spectroscopy, which is a technique, it's also to identify phases, but it works a little differently, where you shine a laser on your sample and you look at the slight changes in that laser's energy due to different allowed phonon modes based on rotation and vibration. And it kind of gives a unique fingerprint for every chemical phase you want to look at. And if we go through and we label these chemical phases, what you can see is there's a lot going on here because there's a lot of different metal sulfide phases that'll form, but generally for the lower temperature anneals, you're forming binary and ternary metal sulfides. And then for higher anneal temperatures with increasing time, you see more and more of these CZTS phases. And if we go on to looking at the morphology of these precursor films, you see a typical precursor morphology for nearly all the films is pretty unremarkable, but for this highest anneal time and temperature, this 500 C for 3 minutes per layer, you see these agglomerates that form. And if we zoom in on these and look at them with EDX, which tells you the elemental composition of a film during SEM, during scanning electron microscopy, you can see that they're rich in sulfur and tin. And if we compare this to the Raman data, the picture becomes clear is that at this highest temperature, you form tin sulfide that precipitates out of your film. And this is related to that decomposition reaction I showed you a little earlier. So what effect does this have on the selenized films? Well, this morphology persists after selenization, and this leaves raised voids, which will be detrimental to device performance, as you'll see in a little bit. So you want to avoid this tin sulfide formation. Looking at more morphologies, you can see there's quite a bit of difference in the morphology after selenization depending on the anneal profile before selenization. You see the fine-grained layers here in the low temperature cases, but at the higher temperatures you see there are multi-layer morphologies, but the grains aren't quite as fine. In particular, this case of 400C is very representative of a lot of the films we've seen in the literature that gave these low efficiency devices. So I'm really to understand what's causing the fine-grained layer in this 400C case. But to really dig into what's going on in these films, I implemented a technique called glow discharge optical emission spectroscopy, which is a depth profiling technique, which allows you to look at elemental composition as a function of depth by sputtering it into a plasma and then looking at the light that comes off of that plasma. And again, each element has its own unique spectrum that it emits. And so you collect that light, and what you get is a raw signal as a function of sputtering time here for all of our different elements, which is a really powerful technique by itself without calibration, because you can see, if there's particular concentration effects in certain regions. But what really makes this more powerful is to calibrate it. So I spent a lot of time calibrating this. The reason that GDOES needs calibration, a somewhat sophisticated calibration, is because the content of the plasma affects the reabsorption of the emission of other light. So it really requires thinking about the composition of your plasma and the collection efficiency of all the different elements. So I went through a somewhat sophisticated calibration where I sputtered multiple certified reference materials. I ended up doing mass spectroscopy on every sample, and I built a Mathematica program to compile this all together. And the plot looks about the same, but importantly, the y-axis here is an atomic fraction now. And instead of just sputtering time, we're percent depth into the absorber. You can see the moly turning on right here. So this is the absorber of the CZTS, or the metal sulfides that we care about. So this ended up being a full-page figure with 42 panes in my manuscript, but I'm not going to show you all that. I'm just going to show you a subset of that data. You can look at elemental ratios as a function of depth once you have it calibrated in this way. You can look at the sulfur over the chalcogenide ratio, which affects the band gap of the material. And when you look at that, you see this trend actually confirms what we saw earlier with the XRD data, with that peak shift towards higher 2 theta. This is in agreement with that, where we have more sulfur incorporation for the higher anneal times and temperatures. I'd also like to point out a couple other, so this elemental ratio is the chalcogen over metal, the anions over the cations. And what you see is a region of increased selenium right here corresponds with increased sodium. And this maps up pretty well with the fine-grained layers. So what you see is for these fine-grained layers in both the 300C and the 400C case, you see an enrichment of sodium and selenium. And this is tied into another theory that's in the CZTS literature about how sodium polyselenide can improve grain growth. And I have a theory that I hope to work on in future work, where I look at how sodium polyselenide facilitates the removal of impurities, actually acts as a fluxing agent. In addition, I wanted to look at carbon and nitrogen. Wanted to show you that because I think this is a really interesting trend. So for 300C and 400C, these green and blue traces here, in the precursor films, they stay about the same. They stay trapped in the film. But as you go to 500C, they're increasingly removed from the film with increasing anneal time. However, after selenization, you only see the trapping of the carbon and nitrogen in their intermediate temperature at this 400C case. So this was kind of perplexing to me for a while, but it is starting to reveal what's going on in this fine-grained layer that we see a lot in the literature that's been really hurting device performance. So to really dig down on what was happening in this fine-grained layer, I did a technique where I fixed a second substrate to the top of a grown CZTSE film, and then I did a lift-off where I'm looking at the fine-grained layer from the top down. I did SEM of this layer, and I did Raman spectroscopy, which revealed that this is composed of amorphous carbon nitride. And after doing some digging in the literature and thinking about this, I can attribute it to the polymerization of thiourea decomposition products, where you form this melanine intermediate and the amorphous carbon final product here, which is inhibiting this grain growth. I'm just going to go through the device data here because it seems like I'm running out of time. The big takeaway from the device data, it's quite a bit. There's a number of small conclusions you can draw, but obviously the films with the fine grain layer have worse power conversion efficiency, and the ones at 500C are higher efficiency. So when you don't have this fine grain layer, it improves efficiency. And the reason for that is that the fine grain layer causes higher series resistance to your devices and a worse diode quality factor. Basically, the squareness of this curve is worse. And there's a number, the 500C films also have better open circuit voltage and short circuit current. And the champion device from this data set was 10.7% efficient, which isn't a world record, but it gives credit to this data set that we could make a decently high efficient device for CZTS. So in conclusion, I just like to give the sort of chemical overview here. I didn't talk about chloride at all, but that's another big part of the picture here. As you increase your thermal exposure during annealing, if you drive off these carbon and nitrogen compounds before salinization, they don't get trapped in the same way. However, at low temperature, they don't seem to polymerize in the same way, and you can drive them off during salinization as well, which is something I hope to pursue in future work, where I look at these low temperature anneals before salinization. And finally, I just like to say that thiourea is really commonly used in a lot of different PV absorber fabrication processes. And this is kind of the first time this decomposition pathway has been put together with this PV work. And I think it's going to have implications for a lot of people who use thiourea in these solution processes. And the thing is this one doesn't need to succeed. Only one needs to succeed to revolutionize the PV market. And if we get that 15% with any of these technologies, it would be a game changer. So with that, I'd like to acknowledge my co-authors and the rest of my group and a couple other people who've been really important in helping me with this work, and I'll take any questions. Yeah.
So how quickly you are enabling these materials matter, right? Like, is there a ramp rate associated with?
Yeah, that's an excellent question. You know, I've thought a lot about this anneal profile, and obviously, if you set something on the hot plate, it's going to ramp up in temperature over time. It looks, in the experiments I've done with, like, you can use an IR thermometer. It achieves the surface temperature. We actually bought a completely different hot plate with like a closed lid, like a very fancy hot plate with a thermocouple to very precisely control the temperature as best as possible. And I tried to, you're doing this over and over again. I try and keep it as constant as possible. It's about 20 seconds it takes to ramp up, I'd say. So that's well below any of these anneal times. But there's obviously some dynamics going on here. I think the ideal system would be like, a pizza oven type thing where you set it on and it goes through a roller, and that way you have a very defined, anneal. And I think that's what would happen on a roll-to-roll type system. You would have very precise control. And this is sort of pointing to the anneal profiles that are optimal for that. Yeah, Brian.
What are the physics behind the fine grain structure that leads to this increased resistance? And I assume there's some electron recombination or something that's leading to that reduced.
Yeah. So you notice that the fine grain layer has, well, obviously fine grains, which means more surface area per volume. And the surface of these grains they're not benign. So just the surfaces themselves can act as recombination centers, but the carbon nitride itself could act as recombination centers as well. And, but I think the biggest thing you saw was not, in the current or the voltage, but it was actually just in the series resistance. It acts as a very resistive layer, which reduces your fill factor from that angle as well, not necessarily just recombination. Thank you.
Thank you, Jack, for another great talk. For the next hour, we're going to be hearing from Dan Truskett, our
highly accomplished inventor and leader in the nanoimprint lithography industry. She led jetting technology development efforts at Canon Nanotechnologies and is currently